Okay, so we're going to be talking about centripetal force. The first thing to be aware of is that the centripetal force is actually not a force. It is the net force. It is made up of the sum of all the other forces in play on an object. So that means that the centripetal force can actually be different from object to object. So let's start with that. So Fc, which we'll designate as the centripetal force, is equal to the net force of all the forces acting on an object. We already know three equations for finding centripetal acceleration. The first one is that. The second one is this. Sorry. And the third one looks like this. So we can very quickly develop equations for centripetal force by using Newton's second law, which is Fc is equal to ma. So if we know the a, which is, in the first case, v squared over r, this is our first equation for centripetal force. And then the other two come from adding mass in the equation. So let's look at some examples of when centripetal force is different. So the first example I'll use is the example of the Earth and the Sun. So if this is the Sun and this is the Earth travels around the Sun in more or less a circular motion. The centripetal force is equal to the force of gravity. So this is the force of gravity. So when we draw free body diagrams of objects, we don't draw the net force. So it would be inaccurate to actually say that the centripetal force is on this drawing. But we just got to keep in our mind that in this case, F net is equal to Fg. It's the only relevant force here. And that means because it's in a circular motion that Fc is equal to Fg. For example 2, we could talk about a roller coaster. If you're on a roller coaster and you're at the top of a hill on the roller coaster, you could kind of represent the hill as sort of part of a circle. And if this is your train car here, there are two forces here, force of gravity and the normal force. Well, notice that the net force between these is equal to the normal force, which is up, minus the force of gravity. If we assume this is a circular path, then we'll replace F net with Fc. And we know that Fc has to be a non-zero value, and it's pointing in the direction of downwards, because otherwise the object won't be going down along the hill. Instead, if Fn 1 over Fg, then it would be curving up. And that's what happens at the bottom of the hill. If you continue that, if the roller coaster was going at this position, and we assume that this is kind of a circle, then in this case, the normal force would have to be larger, but the equation would still be the same. So the centripetal force changes depending on where we are, and the normal force changes depending on where we are. And we experience that when we're on a roller coaster, because when we're at the top of a roller coaster, we don't feel the seat at all because the normal force is practically non-existent. But at the bottom of a hill, when the normal force has to try to drive us up to move up the hill, then the normal force increases, and we feel that as the seat kind of pushing into us. For example 3, I like to use the example of a top-down view of a race car. So this is our race car. Those are the wheels. And the race car is driving in a circle. Well, what's forcing the race car into this circular shape? The easiest way, the easiest way to think about it is imagine that the road was made out of ice. It would be very difficult for the race car to travel in a circle at all. In fact, it would be flying off tangentially. So that means the force that keeps the race car in a circle is the force of friction. So in this case, the force of friction is equal to the net force, which is the centripetal force in this case. So let's do a practical example. We have a kilogram stone whirled vertically with frequency 0.5 hertz on a string 1.2 meters long. What is the tension of the string when the stone is at A, the top of the swing, and B, at the bottom? So let's start with the first part where it's at the top of the string. So we'll just draw a quick picture here. This is the stone. This is the string, but we're going to now have the tension force. So the tension is pulling the stone down. And there's also the force of gravity, which is pulling the stone down. So there's two forces acting on this. The centripetal force is also down because the net force has to be in the downward direction in order for this thing to start to accelerate in the downward direction. So let's plot our givens here. We have the mass of the stone. We have the frequency. We have the radius. So we'll create an Fnet statement. So Fnet, which is equal to Fc in this case, is equal to the tension force plus the force of gravity. Now I'm going to say that down is the positive direction because all the vectors are pointing down in this case. So down is positive. So let's fill in what we know. Fc, we're going to choose an equation that involves frequency. So we'll choose the frequency equation, the centripetal force equation that looks like this. And it's equal to T, which is what we're looking for, plus mg. So we'll rearrange. Solving for T. And then we'll make our substitutions. And this gives us 2 newtons. So therefore the tension is 2 newtons. If we do part B, so we have the exact same setup in terms of givens. The only difference is that we are going to be at the bottom of this circle. So the tension force is now pointing up. The force of gravity is pointing down. And so our Fnet statement is going to look like this. So now I'm going to make down negative again. And my centripetal force, or my Fnet, is in the upward direction this time because you can see that it's starting to swing upward on its journey. So we're going to solve for T again. And this, we're going to use the same formula as before. Notice that instead of subtracting the 2, we're adding the 2. So we'll get 4 pi squared 1, 1.2, 0.5 squared plus mg, so 9.8. That's equal to T. And this works out to be around 14 newtons. So it makes sense that the tension force increases as it goes down, or as the rock goes down, because it has to pull up the stone against gravity. Whereas the tension decreases because its goal is to get the stone down and around, but gravity can do most of that work. So the tension becomes kind of slack. And if you can imagine that in your mind, you'll notice that when if you're whirling something like this, at the bottom of the swing, that's when you feel Newton's third law. It's the object is pulling back on you, but at the top of a swing, it's even possible to get the stone to sort of start to drop down, and the string itself kind of becomes lax and kind of loose.